Welcome everybody back once again to the Mabee Observatory right here at Bethel College. My name is Caden MacArthur and I'll be once again talking to you about parts of our observatory and a target for our new open house event, the Andromeda Galaxy.
So to begin this video, we'll be going over a camera which allows us to take pictures of space that you see just about everywhere in the Science Center here. For example, all of these pictures seen here were taken by this very telescope here at Bethel. But what type of camera do we use to take these sort of pictures? Well, it's this massive thing right here. This camera has many functionalities to it that allows us to take pictures just like these. And to explain a lot of the functionalities of these types of cameras, some background knowledge is needed about normal cameras that you might use every day. In a nutshell, a camera is simply a sensor that collects light, and each pixel is assigned a value of light depending on the amount of photons that hit each pixel. The camera then sends off the information to be processed and generated into an image on the screen. On our camera here, it is slightly simpler since it only collects black and white. And in order to bring out some of the brightness of the structures we're imaging in space, sometimes we need to expose the sensor anywhere from 60 to 300 seconds to allow the camera to pick up as much light as it can from the structure. This can lead to another issue, star trailing. This topic has been talked about in a past video, but it is the result from the Earth spinning on its axis, which causes the stars to move in the sky. Having the sensor exposed to the same spot in the sky while the Earth spins will make the stars not have their normal uniform circle shape. We fixed this by using software built in the telescope to track the stars to minimize the trailing. If you want to learn about star trailing, our first video explains just a little bit more. Being able to take images over time like this allows astronomers to make certain scientific assumptions and discoveries about what they are imaging. One simple example of using light to make discoveries is when we search for transiting planets around other stars. A transiting planet is when a planet passes between us and a star. When a planet does this, a very small dip in the light levels can allow astronomers to possibly determine the size of a planet. And in more complicated cases, a transiting planet allows astronomers to determine the composition of the atmosphere of the planet due to the different wavelengths of light that are being passed through the planet that then reach our camera sensors. This, as of now, is the main way astronomers are finding new planets outside of our solar system every day in observatories just like the one here at Bethel. All it takes is patience and luck. However, no camera is perfect. Even the most expensive NASA-quality cameras have their own issues. Here is a picture taken simply of nothing. Our lens cap is on the telescope, but what are all these white spots? And what is this giant line that appears in the picture? Is this camera broken? Well, to simply put it, even with all these artifacts, this camera works just fine. This image is called a dark, and we use it to calibrate our images when processing them. This image allows us to see all the imperfections in our camera sensor over time. These white spots around the camera is either called noise or hot pixels. These occur because the sensor thinks that in those spots the pixel is taking in light, but instead it is simply a bogus signal from the pixel caused by lingering electric charges that can come from various sources. And these lines are massive columns of pixels that are simply bogus. You might be thinking, why do we still use this camera even with all these defects to it? And to simply put it in 3 parts, 1, this camera is insanely expensive and was graciously donated to us, and we simply do not have the funds to get another. 2, even if we did get another camera, there's no telling whether it'd be worse or better. And 3, we have means of getting rid of these artifacts when we are imaging. A camera with this amount of artifacts is still a very good camera. This is probably actually how it came from the manufacturer, since it is very hard to get a perfectly working sensor overall. But how do we mitigate these artifacts? Well, one way to reduce the noise is to simply cool the camera. We cool the camera to around negative 40 degrees Celsius when imaging, and this mitigates some of the noise present. But what about the lines? These lines are often calibrated out in our program that we use, which will be explained later. Along with that, we do not shoot at the same exact spot. We use a technique called dithering where we shoot. This means that we move very slightly each time we take an image to gather information about the entire sky. So by the time we have all of our images needed, we can use our program to average out the light values of each pixel and our lines will go away. We then combine our lights, darks, and a couple other calibration images together with our images we took, and our program called Deep Sky Stacker automatically lines up the stars for us so we can further process our image. But there is still another large aspect of the camera that I have yet to cover, and that is the filter wheel. This filter wheel allows us to observe specific wavelengths of light given off by specific elements in space. For example, if we wanted to look just for hydrogen, we would move our filter to the hydrogen filter and take an image. But let's first get a flat image of our filter so we can then calibrate our image. But wait, what is all of this? These donut-looking artifacts are dust particles stuck on the filter, and there is nothing we can do to get them out of there. And these are present on each and every filter on our wheel. This type of image that we took to see these are called a flat, which is another one of our calibration images. And they are created by putting a panel of light in front of our telescope to get the same amount of light level for each pixel. Doing this allows us to see where our dust is, along with where our camera begins to vignette around the outside due to a square sensor looking through a circle hole. This allows us to use these images to calibrate light levels where these dust particles are to get a clearer picture of our sky. But why do we need this filter wheel if everything is in black and white? Well, as I said before, this filter blocks specific wavelengths. But how do the images on the walls come out colored if the camera only takes black and white images? Well, to say it simply, the colors on the walls are just made up. After sending all of our pictures through our program to average out our image, we still get left with a black and white picture. So depending on the filter you took this image in, you would color it a specific color to your liking. Normally, you would have one filter image you would color red, then another blue, then another green. There is no rule on what color an image has to be, it is all up to you. We then put these images together in Photoshop, and bam! That, in a nutshell, is how we and nearly everyone else in astronomy gets our images to look the way they do. Further questions about our camera can be asked during our new upcoming open house, which will be focusing on imaging the Andromeda galaxy. Andromeda is the closest galaxy to our own Milky Way galaxy at only a small distance of 2.5 million light years. To put that into perspective, the furthest launched probes into space right now are the Voyager probes, which began their journeys in 1977. These probes have yet to reach a light day distance from Earth in their 46 years of travel. Andromeda is also the largest galaxy in our local group of galaxies, holding about twice as many stars as our own galaxy. Its discovery is credited to a Persian astronomer in the year 964 when the astronomer spotted a small smudge in the sky. In very dark skies, Andromeda can be seen with the naked eye. However, you won't be seeing any of its colors or spirals. Instead, you would be seeing just a smudge of gray-blue color. Around this time of the year, Andromeda is nearly directly overhead starting around 8 p.m. Now that our camera is on the main telescope, we will not be able to look through an eyepiece at Andromeda like previous open houses. But we still have our smaller telescope on the deck pointed at various targets in the solar system. For this open house, we will be imaging Andromeda, like I said, and processing the images taken into a real final image throughout the duration of the open house. And that is about all I have here for you guys. Our open house will take place on either Thursday at 7:30 or Friday at 7:30. Partial cloud cover is expected for both days, so be on the lookout for announcements through your email for a definitive date. So feel free to come up and ask questions about our imaging process as we take some of our first images this semester right here at Bethel College.